Recording this. Let everybody know. Fantastic. And I'm just going to give you a brief introduction to our 4 speakers this evening, and you will find more information when you look at the web page that you went and you registered on this evening. So we're going to be starting off tonight with Andi Thomas. And Andi has been a part of the NASA community since 2015, and she currently serves as the project manager for the Web Strategy and Communications team for NASA's Earth Science Data Systems program. After Andi, we're going to hear from Dr. Sarah Ringerud. Sarah is a research meteorologist specializing in remote sensing and atmospheric science, and Sarah currently serves as the deputy project scientist for the Global Precipitation Measurement Mission. Then we will hear from Dr. Amita Mehta, whom I've had the pleasure of working with for over a decade. And Amita is a research associate professor and applied research scientist at NASA and at the University of Maryland, College Park. And she serves as a lead instructor in NASA's Applied Remote Sensing Training, or RSET program. And then we're going to finish up with Roland Kays. And Roland is the head of the Biodiversity Lab in the North Carolina Museum of Natural Sciences, and he is a research professor in forestry and environmental resources in North Carolina State University. So without further ado, it is a joy and a pleasure to get started with Andi. And Andi is going to give us this broader overview of what it is we're talking about when we're talking about remote sensing. And Andi, I will wait and be sure that I let you know that we can see your slides before I abandon you. And as I imagine you heard, you've got people from all over the world here come to learn more about remote sensing.
Hello, everyone. Can you hear me?
You sound good. You sound maybe if you got a little closer to the microphone, that could be helpful, but otherwise you sound good.
Just turn. All right. Can you hear me a little bit better now?
We hear you better now. Yep.
Okay, great. And then here is, can you see my slides?
I see your slides. You're not yet in slideshow mode, but I'm watching them. I'll let you know as soon as you get there.
Okay, great.
Awesome. You're on. All right.
Perfect. All right. Well, good evening, everyone. For those of you that are in the East Coast time zone or close to it, I'm Andi Thomas, the Web Strategy and Communications Team Manager for the Earth Science Data Systems program. I'm actually coming to you from, I came back from DC today. I just flew in an hour or so ago, and I actually live in Knoxville, Tennessee. But I'm originally from Texas, so I see all of you from Texas, and just want to give a nod to my fellow Texans out there. We're going to cover the remote sensing basics tonight. And so what is remote sensing? We'll talk about orbits, the electromagnetic spectrum, instruments, as well as the 4 types of resolution that we are interested in. So first off, what is remote sensing? Remote sensing is the acquiring of information from a distance. So in other words, gathering information about something without touching it. One really familiar way is if you take out your iPhone or your Android and you snap a photo, you're sensing something without touching it with your phone. And NASA does this from of Earth and other planetary bodies via remote sensors on satellites or platforms and aircraft that detect and record reflected or emitted energy. We have a ton of platforms that are remote sensing platforms, and so here is the Science Mission Directorate at NASA's Science Fleet for operating in future platforms. And there on the left, you can see all of the Earth platforms. But if because I'm with the Earth Science Data Systems program, this Earth fleet is near and dear to me, as well as my colleagues here. And so We have a ton of satellites in our Earth fleet that are either coming online or have been online for a very long time within NASA. And as you can see, all of these satellites or platforms with all of their instruments or sensors are orbiting the Earth. So let's talk about orbits for a second. There are three main types, and they're typically classified by altitude. And so the first one is if you're in high Earth orbit, so you're at a high altitude, greater than 35,000 kilometers above the Earth. So if we're thinking about high Earth orbit, that would be where a lot of our weather or communication or navigation satellites live, versus our mid-Earth orbit or medium Earth orbit is approximately 2,000 to 35,000 kilometers above Earth. And that's where some of our navigation, like our global positioning system satellites are. And then there's low Earth orbit, or fondly called LEO, which is approximately 160 to 2,000 kilometers above the Earth. And that's where a lot of our NASA Earth observing satellites live. So one thing to keep in mind is that satellites that are orbiting at 35,786 kilometers are at an altitude where their orbital speed matches the planet's rotation and are in what is called a geosynchronous orbit, in sync with the Earth. In addition, a satellite that is in geosynchronous orbit that's directly over the equator will have a geostationary orbit. So a geostationary orbit enables a satellite to maintain its position directly over the same place on the Earth's surface. So let's talk about eccentricity and inclination. So orbits, as you can imagine, orbits that or satellites that are in a higher altitude are they have a longer distance to go, and so they have a slower orbit time. Versus when you're at a lower altitude, you have a faster orbit time. And eccentricity is the shape of orbit or deviation from a perfect circle. So if you look at my slide on the bottom right or left, depending on what your mirror looks like, you'll see an E equals 0, or an eccentricity equals 0 is where you're orbiting in close to a perfect circle, versus when you're getting closer to 1, it only goes up to 1, you're orbiting in a less than or an elongated or oblate spheroid circle. And so the shape of the orbit or deviation from a perfect circle is your eccentricity. Versus inclination is the angle of the orbit related to the equator. So you look on the top right of my slide, you can see that the Earth's rotation, if you're looking at the equator, you're at 0, versus you're going closer to the poles, you're at 90. So we in Earth data, we call sensors our instruments, and instruments are aboard satellites and an aircraft, and they use the sun as a source of illumination, or provide their own source of illumination for measuring energy that is reflected back. So passive sensors are what include different types of radiometers that and spectrometers that are designed to detect, measure, and analyze the spectral content of reflected electromagnetic radiation. So most passive instruments they're using natural energy from the sun, and they operate in the visible, infrared, thermal infrared, and microwave portions of the electromagnetic spectrum. And we'll get into what I mean by electromagnetic spectrum in a minute here. Active sensors provide their own source of energy. And so active sensors include different types of radio detection and ranging sensors, altimeters, or scatterometers. And a lot of our active sensors operate in the microwave band. And they're useful for measuring vertical profiles of things like aerosols or forest structure or precipitation, ice, and a couple of other things that we measure a spectral signature of. Okay, big words, right? The electromagnetic spectrum, or EMS. So electromagnetic energy is produced by the vibration of charged particles, and they travel as waves through the atmosphere and the vacuum of space. This is, you're looking at this slide here, a picture view of the electromagnetic spectrum. We can't see these waves unless you're in the visible wavelengths. So there's different wavelengths, and we measure the wavelengths from wave crest to wave crest, and they're in different frequencies. And so a shorter wavelength means a higher frequency, so looking towards the right of the slide, versus a longer wavelength is a shorter, excuse me, a longer wavelength is a shorter wavelength. Yeah, sorry, my brain. So visible light sits sort of in the middle of that range of the long and short wave radiation. And there is that small portion that you see in the middle there of energy that the human eye can actually see. And instrumentation is needed to detect all the forms of electromagnetic energy. And so NASA instrumentation uses this full range of the spectrum to explore and understand our processes that occur here on Earth and other planetary bodies. The primary source of the energy observed by the satellites is the sun. And the amount of the sun's energy reflected depends on the roughness of the surface and its albedo, which is how well a surface reflects light instead of absorbing it. So you think like snow, when you're out in the snow, if we have some skiers out there or snowboarders, when they say high albedo and you're protecting your eyes from the albedo, so you're not only protecting your eyes from the sun coming down, but also you're protecting your eyes from the sun coming up from the snow and being reflected back up. And so if snow has a very high albedo, then on the opposite end of the spectrum is the ocean, right? So the ocean has a high absorption. And so with the ocean, you're only reflecting like 6% of the incoming solar radiation, and you're actually absorbing the rest. And so you're not getting that high reflectance in the same way. So everything on Earth either reflects, absorbs, or transmits energy, and it varies by wavelength. So, and then everything on the surface of the Earth has a spectral signature, just like your fingerprint. You have your signature. Every fingerprint is unique. It's a measure of identification, and just like that, the soil, the plants, the animals, like we'll talk about later, all have their own spectral signature. Okay, I hope everyone's still with me. Let's talk about color theory for a second to make a little bit better sense of what we're seeing when we look at satellite data from sensors. Color theory. So subtractive color theory is when the more colors you put together, you eventually get black. So think when you were a kid, or if you have kids. I have a 3-year-old, and when he's finger painting, if he uses all of the colors eventually, which happens every single time, eventually your color is black. And versus the opposite, where it's additive, where the presence of all colors of light is white, versus if you have no light, it's black. And so sensors are additive. Think of sensors, additive color theory. Think of paint, subtractive color theory. So for example, when you look at a leaf, you see green reflected off of the leaf. And if you look at this graph here of the spectral curve, you can see from violet to red, green being in the middle, and a high reflectance. And you're seeing, just like the lorem ipsum in the middle, sorry there. So you're seeing green with your eyes. You're perceiving green based on the wavelength. Okay, So this is, if you're looking at the spectral signature or the spectral reflectance of different things on the surface of the Earth, and you're looking at it at a logarithmic scale, this is kind of showing you, okay, a high percentage of reflecteds would be snow and ice versus low would be water. And then you see some things in the middle. If you look at the like needle leaf vegetation or broadleaf vegetation in the middle there, there's a really unique measure for vegetation. They call it the red edge, where it kind of leaps up for healthy green vegetation at near infrared. And but you know, we'll get there. That's down the road. That's another difficulty level of remote sensing. For now, you just need to know that everything that we see on the surface of the Earth has a spectral signature that's unique, and all objects with a temperature above 0 reflect and emit energy that radiates through space. And also, the entire electromagnetic spectrum consists of the longest wavelengths, like radio, or the shortest ones, like gamma rays, and then there's everything in between. And to observe Earth from a platform or satellite, the instruments or sensors are designed to detect the visible and infrared wavelengths. Here's another look at the a graph with the spectral signatures for and just things that we know in general about things that are have very specific spectral signatures, where we can kind of identify where there's chlorophyll absorption, and see that nice red edge going up at 0.8 to or it's usually around near infrared 1.3. So a little bit moved over, 0.8 to 1.3. And then versus your water absorption points. And then you can kind of glean as a scientist what's corn versus soybean based on their spectral signatures. All right, so I'm going to run over time, and I'm so sorry, and I'll go really fast. All right, so the 4 types of resolution. Like I said, this is an entire college course, so here we go. Radiometric resolution, the amount of information in each pixel, and the number of bits representing the energy recorded. So it's usually each bit is recorded as an exponent to the power of 2. So if you see in the picture here, a 2-bit would be 2 to the power of 2, so it has 4 values, versus an 8-bit would be 8 to the power of 2, which would be 256 values. And the higher the radiometric resolution, the more values are available to store information. And so you're able to provide better discrimination between slight differences in energy. So like when assessing water quality, the radiometric resolution is necessary to distinguish between subtle differences in, say, like ocean color or chlorophyll. Then there's spatial resolution. So spatial resolution is the size of each pixel within an image, and the area on the Earth's surface represented by that pixel. And so like you can think of when things are, if you ever have like a picture that's loading and it's very pixelated, so it has really coarse pixels, that would be a low spatial resolution. So you're able to see, glean way less detail than fine or a high resolution, where you'd be able to see like buildings or neighborhoods. And so like 10-meter resolution is better than, say, like 30-meter resolution. But don't get hung up on the spatial resolution when you're looking at data sets, because it's not always the best to have the highest or the finest resolution. You kind of have to think about what science question you're needing to answer before you get into resolution, because there's a lot of really great data that's available in like the mid-resolution levels for spatial that might do you really well for assessing land cover change over time, for example, at a different scale than looking at buildings or neighborhoods, or you might not need to. So versus spectral resolution, which is our third resolution that we're studying. So it's the ability of a sensor to differentiate between finer wavelengths. And so in college, I'd always think spectral resolution, number of bands. And it's been a while, and I still think spectral resolution, number of bands. So the number of bands in your satellite data. And temporal resolution is the time it takes for a satellite to complete one orbit and revisit the same place over again. So I'm going to leave that one there for a sec. And I don't think, Dorian, you can give me permission or not. I don't think we have time to watch 30 seconds of a video, but if we do, and if we don't, you can just look at this later.
Okay, we're fine. You can go ahead and do it. You're just fine.
Okay, awesome. Great.
Yep.
Okay, let's do it. So what I didn't want to, I wanted you to have a different voice in this presentation other than me for the basics of remote sensing, because this video is like 10 years old, but I still refer back to it because it's excellent. And it's from NASA Goddard, and it will show you peeling back Landsat's layers of data and give you a perspective of taking remote sensing resolutions and orbits and into account to create satellite data that we use to measure information on the ground from space. We'll let this load, and if it doesn't, then I'll give you another. Actually, I'm going to go over here. Let's see. So, new share, window. Can you see my screen?
Yep, you're looking good. Awesome.
Okay, great. And you can hear the video?
The video actually is it's impossible to hear. It's kind of all jarbled. You might have to talk over it. We're not really able to hear any of the sound from the video.
Okay, no problem. So I'll improvise. Can you hear me still?
Yep, we hear you. You sound good.
Okay, so this is showing that Landsat and how whenever we click or whenever we are collecting data from the Landsat satellite, it's giving us different bands at different wavelengths that provide different information. And so we have blue band, green band, or my professor would finally in college would call it the color guns, the blue color gun, the green color gun, and red and near infrared versus shortwave infrared 1 and 2. And so you can kind of see all of those wavelengths in bands that are collecting basically a stack, or they call it the onion layers of information. So you can't just have one, or you could, but it's better to have be able to extract different layers to get different depictions of the Earth's surface. And so if we're flying over with Landsat imagery of Florida, and you're looking at natural color imagery, so what you see with the naked eye, then this is what you would be seeing. And so you can see city and ag, you can see water, and this is all with the blue, green, and red band, and they're all working together to provide what you're seeing whenever you actually look at the surface. You can also get other wavelengths, pull out other wavelengths from the data and get different features of the land surface based on what we know about their spectral signatures. And so the same data, but different wavelengths. We're flying over the Everglades, and you get with multispectral data, you can see the difference between what a tree is versus a shrub versus water versus a marsh. And so you're getting a little bit more information. So the more, the higher spectral resolution, the more information you're obtaining. Okay, so So here's what we're doing. So if we fly over the same location, but we're using the infrared sensor, you're getting a lot of reflected light in the near infrared because what? There's a ton of vegetation, a ton of healthy vegetation. And so you're getting a spectral signature that's showing a lot of near infrared, or that red edge that we talked about earlier. I'm going to go ahead and stop there because that's really the point I wanted to make, was just pulling it all together with your knowledge now of resolution and orbits and all of the satellites and the different needs that they're meeting for scientists and decision makers, and then I'll pass it on to someone else.
Thank you so much, Andi. You know, I saw, and if you look in the chat, there were a few questions for you. I saw a couple people writing that, you know, this is awfully complicated. Today I was teaching gifted and talented middle school students about the electromagnetic spectrum, and I had a full hour. And even then, we barely touched the surface. But I love this idea of the, you know, think about the fact that we all have our own unique fingerprints. And this idea that if you take all of the known elements in the periodic table, we actually can see the fingerprints or the spectra for each of those. So just imagine the things we can do now that we understand how to read these fingerprints, this way of understanding what we're looking at without actually directly touching it. Awfully complicated, pretty darn fascinating. And so when you get a chance, dig into that resource pack. And I'll keep adding the link there because there's just so much rich information. And next, we're going to hear from Sarah. She's going to tell us about the GPM data. And then Amita is going to tell you some of the ways that you can get on and get more training in any of these areas that you might be interested in. And a lot of it is virtual. Most of it is virtual. And so you can get on there and do it in your own time. So that was wonderful. And let's see, Andi, if you will stop sharing.
Yeah, I just need this stuff.
Cool. All right, awesome. And thank you so much. That was fantastic. That's a huge topic to cover. And as Andi said, she's just flown back. Well, our Sarah, she is flying off to Tokyo tomorrow. So or at least to Japan tomorrow. So we certainly have a group of dedicated folks here to learn, but also some really dedicated folks here to teach. We're very appreciative.
Let's see, this worked earlier, but it's not giving me the option of my PowerPoint. So I'm going to share my screen and hopefully we can make that work.
Andrea will take care of it because she, I think, downloaded your slides. Yep, looking good. Looks great.
Good. Okay, fantastic.
All right.
All right. Well, welcome everyone from all over the world. It's wonderful to be here. As Dorian said, I am the Deputy Project Scientist for the GPM mission. This is the GPM webinar series. Let's see if I can get rid of this guy. Oh, what did I do?
It looks good on my end still.
It's gone on my screen.
Oh, gracious.
Sorry about that. Okay, is it back?
Yeah, we see it.
Okay, and you don't see the Zoom window?
No.
Okay, fantastic. Sorry about that.
No, no.
Okay. But yes, I am the Deputy Project Scientist for GPM. This is the GPM webinar series. Hopefully you all have some sort of familiarity with the Global Precipitation Measurement Mission, which has now been orbiting and collecting amazing science data for 10 years, which is very exciting. And so I'm going to talk about remote sensing very specifically from the platform of the GPM core satellite. And this satellite has really been an absolute game changer in precipitation remote sensing. So this is a schematic of the GPM core satellite, and you can see that along with, solar panels and avionics and a propulsion module that are keeping this satellite in space, there's two main instruments here that are collecting the science data. So if you look on the bottom, there's this big kind of shiny rectangle. That is our dual frequency precipitation radar. And we have a Ka band, which is at 35.5 gigahertz. This is all in the microwave spectrum. I want to thank Andi for that excellent introduction to remote sensing. That was perfect perfect series to have these back to back, and the KU band at 13.6 gigahertz, so a little bit lower frequency, higher wavelength there. So that's this rectangle on the bottom. And then you'll see my favorite, this cute little guy in the middle that sort of looks like it's wearing a hat. That's the GPM microwave imager. This is our passive remote sensing instrument, and I'm going to tell you all about these two guys. All right, so Andi talked a little bit about active versus passive remote sensing. So the radar is an active sensor. It sends out radiation at a specific frequency. And the frequency we've chosen for this is in the microwave because that is the appropriate frequency for interaction with water. And so we're wanting that radiation to interact with hydrometeors, which are raindrops and snowflakes, particles of water in the atmosphere. So these waves travel from the spacecraft down towards the Earth's surface. They interact with the hydrometeors and other particles in the atmosphere, and then that radiation is reflected back to the radar, which then measures what comes back. And based on that reflective signal, we can derive the location and the intensity. So it basically can tell us how much stuff is in a volume that's being measured. And there's a little bit of an issue there because if you think of a volume of air where it's raining or snowing, you could have the same amount of water in that sort of cube of space distributed in different ways. So you could have a whole lot of really small raindrops, for example, or just a few large raindrops and have the same volume of water. So we want to be able to tell a little bit more. So we need two pieces of information. And this is why we have the two different frequencies, that KU and KA band. By having that extra piece of information, we can differentiate those things a little bit to be able to derive a very accurate rain rate. So this is kind of a fun animation from Randy Chase that shows this overpass of the dual precipitation, the dual polarization radar over a typhoon. And so you see on the right there, the plan view of the reflectivity. So you can see this beautiful swirling storm. And you see the line animated going across. That shows you where these vertical plots on the left-hand side are coming from. So you can see at the very top, that's the reflectivity coming in the KU band back to the spacecraft. So you can see these really cool towers associated with the bands of this storm. The KA band is below that. So a little bit higher frequency, a little more attenuation, a little less reflectivity. And then the bottom panel there is the dual frequency ratio. So this is the relationship between those two frequencies, which, as I mentioned, gives us that extra piece of information that can tell us something about the size of the drops and the number of them. So that's the active sensor. And then the passive sensor, the microwave radiometer, this is the instrument that I've spent most of my career working on, so it's very near and dear to me. And Andi kind of said that everything that has a temperature is emitting some amount of microwave radiation. And so a passive sensor is measuring that emitted radiation. And when we choose frequencies to measure that are sensitive to water, that passive radiation can tell us about the amounts and character of any kind of water that it's looking at from the surface. So we can use these measurements to look at water vapor, soil moisture, precipitation, anything. Luckily, the atmosphere is not completely, but relatively transparent at these frequencies. So what we're seeing is all coming from, either the surface or the precipitation hydrometeors in the column. And so what we do is we make use of many different frequencies where this radiation might be emitted. So we look at the lower frequencies to see emission from liquid drops, and we look at the higher frequencies. So these are, smaller wavelength to see scattering from ice, snowflakes, and raindrops as well. And then we're able to, based on algorithms, utilizing what we know about how the geophysical variables work, we use algorithms to relate those emission and scattering signals to a precipitation rate. And these are all of the frequencies that are present on the GMI radiometer. We have 13. It has dual polarizations. The polarization is just the orientation of the electromagnetic waves. And by measuring at perpendicular polarizations, that can give us also a lot of useful information. So you can see it ranges from these lower frequency 10 gigahertz channels where we see a lot of emission from liquid, all the way up to 166 and 183 gigahertz where we get a really nice scattering signal from ice particles. And here I want to just give you a little more of an illustration of what those different frequencies look like. So you can see these are some radiometer overpasses across South America, and we've got this really nice sort of linear precipitation structure east of the continent over the ocean. So if you look in the upper left at the 10.6 V pole channel, you see we just have this really nice warm signal over that cold ocean surface that tells us that there are some hydrometeors in that column. At the 19 gigahertz, it's a little bit stronger. You can see a little more definition and structure. The one in the middle here is a water vapor sensitive channel. So you can see the increase in water vapor associated with that area of precipitation. And then if you look at the bottom right, you'll see in that same area, we actually have some blue and light green colors. So it's actually lower brightness temperatures in this area. And that's indicative of the radiation being emitted towards the spacecraft being actually scattered away. So it tells us that there's a lot of ice particles at the top of these precipitating systems. So we put all of this information together and use what we know about how the atmosphere works to translate this picture into a precipitation rate at the surface. So this is what the GPM core satellite kind of looks like in action. So it's flying kind of towards us in this plan view. And you can see the GMI radiometer with the circular antenna there, scanning in a very wide swath across ahead of the spacecraft. The radar is scanning at a narrower swath, looking kind of straight down. And so we're getting these observations nearly simultaneously. So how do we put this all together for science? This is a really cool animation. You can see a very active Atlantic basin in August of last year. And we happened to get a really nice GPM overpass from the core satellite of Hurricane Franklin. So the animation is zooming into that now. And I'm going to pause it here for just a second. So you see in the very wide view, that's the information we're getting from the radiometer. So the radiometer gives us this amazing map of the structure and the size and the extent of Hurricane Franklin here. But it can only tell us the surface precipitation. Down the center of the swath, we have this amazing radar data, which is giving us information in the vertical. So as we zoom in here, you can see the vertical towers associated with the rain bands in this hurricane with very strong precipitation near the surface. And then at the top, as it comes back here, the blue you see is the ice on the very top of these storm clouds. So just an absolute wealth of knowledge coming from the combination of all these fantastic observations from the core satellite. Of course, the GPM satellite, as you're seeing here, is just one little guy circling in LEO orbit. And we really want to get a picture of the global view of precipitation. So the way we do that is there are all kinds of other radiometers flying around the planet all the time. They have different purposes. You know, some are for defense, some are for soil moisture, some are for weather modeling. We go ahead and grab any radiometer data in the frequencies that are sensitive to water, and we use them to kind of morph all together into a global picture of what's going on. And the core satellite is absolutely the key to making these global products. So we use the core satellite as a calibrator to make precipitation algorithms from each of those radiometers from all different, you know, they have different footprint sizes, they have different frequencies, they are viewing angle differences, they're coming over at different times. But we use that amazing core satellite to calibrate all of those into consistent global retrievals. And at the bottom here, I've got a week's worth of iMerge precipitation, which is our level 3 global precipitation product from GPM. This is from actually the last week ending on, I think Tuesday was when I grabbed this. So you can see Hurricane Beryl plowing through the Caribbean there. And I think at the very end, it gets to Port Texas. But so that was just a quick synopsis on the core satellite for you. It has absolutely revolutionized precipitation remote sensing. And I look forward to hearing about what's next.
Wow, what an amazing overview of, the complexity, but also the incredible data that we're able to get. And while you were presenting, there's lots of questions, so you'll be busy kind of answering some in the chat. And somebody asked about, wow, is this used for weather forecasting or for other things too? You have got to join us on September 5th, folks. You are going to be absolutely blown away by the many ways that these data are being used, from things like protecting elephants as they might wander into family farms, to increasing the amount of fresh water that's available in places that farmers are used to kind of emptying out rivers to water their fields, to weather forecasting. It really is incredible what we're able to learn, and really the ways in which people are taking this data and doing things with it. So thank you so much. Super duper exciting. When you look at the resource packet, you're going to see that I've done a deep dive into GPM, into the microwave imager and the dual precipitation radar. So you're going to get a deeper dive into that. So next, we're going to hear from Dr. Mehta, and she will tell you where and how you can access just this wide array of various training, because we know you're all like, oh, this is cool, this is crazy. How do I learn more about it? You're in the right place.
Let me share my screen.
Yep, go ahead and share your screen, and I'll let you know when we see your slides so that you're not wondering.
Do you see my slides now?
We see your slides right now. They're not yet in presenting mode. There you go. Brilliant.
Okay, wonderful. Greetings, everyone from all different time zones. Very happy to be here and sharing this with you. Actually, the first two presentations are perfect leading into this. You learned about overall knowledge about remote sensing, what it is, different orbits and everything. And then you focused on a specific satellite like GPM, core satellite. What I want to talk about, it's a pretty broad view of NASA Earth observations. So this is an overview of remote sensing observations for research and applications. And just overall, we'll talk about a number of observations which are available from NASA. We'll see a couple of applications of GPM data that we have from a few case studies that we work with. And then I'll talk about a training program that I'm a lead instructor with, the Applied Remote Sensing Training Program. So let's start with this animation. Andi showed a number of missions that are currently available from NASA. They're flying. And here you can see in video form different orbits. She talked about a sun-synchronous polar orbit. You can see satellites going from pole to pole. There are satellites which are in low inclination orbit. So you see all these different constellation of satellites flying. These are all current from NASA. And I'm going to walk through a number of satellites which allow us observations of atmosphere, land, ocean in detail. So GPM first, that provides precipitation global. So core satellite, of course, is there, but as Sarah mentioned, iMerge, which is a merged product of many satellites, provides a very consistent global product every half hour at 1/10 of a degree resolution. Then there are missions, Landsat, that you saw a movie from Andi. Current flying satellites are 8 and 9, but this is the longest flying mission since 1972. And it's used, this is an optical sensor satellite, and the current Landsat 8 and 9 also have thermal infrared instrument. So these satellites are used for deriving many geophysical variables such as evapotranspiration, land cover, including water surfaces and water bodies, vegetation, snow and ice. So it demarcates between different kind of land surface. So it's used for that. And also for water quality, it is used. Then relatively like 10-year-old satellite SMAP, it is soil moisture active passive, and that provides information about soil moisture. There are also a number of satellites. A recent one is SWOT, that is surface, water, and ocean topography. JSON-3, Sentinel-6, Sentinel-1. They have altimeter radar. Andi talked about passive and active remote sensing. So GPM has a radar. Landsat is mostly passive. Optical SMAP is passive microwave. And these satellites that we have, they provide, they use microwave radar altimeter. They provide inland surface water height, so in river and lakes, also surface inundation and ocean surface height. They're available from these satellites. Then we have Terra, Aqua, National Polar Partnership Satellites, and Joint Polar Satellite System, or JPSS. These satellites are also polar orbiting satellites with optical and infrared sensors, and they are used to derive land cover, so water bodies can see from that, water quality. Also, they are sensitive to fire detection. They're used for evapotranspiration because they can see vegetation and non-vegetated areas also. They can provide cloudiness information, and very widely used for air quality monitoring as well. Then there is GRACE follow-on, or GRACE, and that is a satellite that provides groundwater information globally. There is ICET-2. This provides information about land and sea ice and water surface height. It provides bathymetry in water bodies as well. A very recent satellite that was launched in February of this year is SPACE, and that is focused on water quality. It has an ocean color instrument. It also has polarimeters. They can be used for looking at air quality. One more satellite that flew, it was launched last year, that's TEMPO, that's focused on air quality, and it measures not only particulate matter that Terra, Aqua, and PPJPSS sensors measure, it also provides trace gases like ozone, nitrogen dioxide, and sulfur dioxides. So there's a bunch of satellites that you can use to look at different portions of Earth system. Similarly, there are Earth system models in which satellite data are assimilated or satellite data are used as forcing, and such models are listed here. So Mehta, that's a reanalysis product from NASA, Goddard, and all these are global products. There is land data assimilation system. That's just a land surface model that is forced by a weather and precipitation data. And there is also a project that provides climate change projection from climate couple model intercomparison project. These are downscale data. And so this is just for your reference and information that all these modeling data are also available, and they provide these parameters. So Mehta is used for winds, humidity. It also has runoff. It all has land surface components, also has chemistry model as part of it, and provides a particulate matter like PM 2.5. GLDAS has soil moisture, evapotranspiration, runoff, something that you cannot observe directly. It has to be either calculated or measured in situ. And so this is the model quantity, but that can be obtained from GLDAS. And similarly, snow water equivalence. So if you have snow, how much water is there, and when it melts, how much water you will get. You can get that from GLDAS. And these are different socioeconomic projections are considered based on IPCC scenarios in next GDDP models. And they all have different resolution. Now, there are about 4 different tables that I won't go into detail because it's talking about the same satellites. Now it's talking about which sensors are on these satellites that we just talked about. So Terra and Aqua has MODIS, and this is mostly for your reference. You can go back and look at it if you want to use this data. What are the swath width? What are the pixel sizes? What's the resolution? What's the temporal coverage? So all these polar orbiting satellites, MODIS, VIRS, then there is a geostationary satellite. This is also used for air quality data. And the TEMPO mission is also in geostationary orbit, which was launched last year, has a UV and visible spectrometer. So these are sensors, these are specifications, temporal and spatial resolution and coverage. These satellites are specifically, they provide satellite air qualities, especially optical aerosol depth they provide. Based on that, particulate matter is derived, and that provides visibility and aerosol concentration in the atmosphere. These are the products that you can also get: smoke, dust, fire, these, and true color images. So just by looking at it, you can see what's going on. This is clouds, this is haze, this is land, this is vegetation. And mainly all of them provide aerosol optical depth. Then satellites for water component, useful again for weather and climate and hydrology. So precipitation, of course, GPM. Predecessor of GPM is TRIM, and combined TRIM GPM with a number of satellites that Sarah talked about, we have very good 20+ year of data now at 1/10 of a degree, 30-minute resolution. So this provides a good climate record, good climatology for precipitation globally. And soil moisture is available globally as well. Landsat satellites, these are the sensors. Again, these are optical and infrared sensors. Different satellites flew during different time periods, but if you look at other sensors, and if you look at Landsat has pretty high resolution of 30 meters, so it's very useful for looking at land cover and high resolution information that you need. Similarly, European Space Agency also shares data with us, like Sentinel-2A and Sentinel-2B, with a multispectral instrument, which is again visible and in optical spectrum. And that also has a pretty high resolution of 10 to 20 meters. And then VIRS, which is similar to MODIS. Finally, these are active sensors on Sentinel-1. This is from European Space Agency as well. And these are Japanese satellites, ALOS. They both have synthetic aperture radars. So we'll see in a few minutes some examples that when you have optical data, they cannot see through clouds. So if the clouds are present, you can't see anything below it. But SAR and microwave data, they can see through water and clouds. So they are useful. They're all weather sensors. So they're quite popular for a number of applications. So this is like a list of all the satellites that you can refer to when you want to get certain geophysical parameter, which satellite you will use, what would be the resolution. So that's for your reference. Now, next couple of slides are going to talk about different tools where you can online go and find these data. You can download. So NASA Earth Data Portal is really is the place to start with. You can take a tour, like get started. You can find data by topics, then use data. So then you can have some tutorial and you can learn how to use this data. You have near real-time data available from these LANs. There is fire information for resource management system or firms. which has active fire data. And you can see that here. And there are a number of data tools. We don't have time to get into this, but you can explore this at your convenience. We'll look at a couple of examples, especially Worldview that covers LANS data. And there are also global imagery browse services that are very useful to look at. So this is like a go-to place to find any data. The different NASA data centers, they hold different, they have repository of different data sets, but you go here and you are kind of guided where to go and how to download the data. So then this NASA Worldview, and if we have time, we'll have a quick demonstration. This is a near real-time interactive tool, and it also has past data. As you can see here in the bottom, you can navigate through time. This particular picture shows Modi's cloud cover, which is shown in white, and I-merge precipitation is shown on top of it. And you can see Hurricane Beryl right here. This is 7th of July, right at, as it came over Texas. You can see the cloud cover here, and this is the precipitation. So you can zoom in here and see different phenomena, different places. You have a number of layers you can choose from. So this is one tool that's absolutely very useful to quickly browse the data. You can also save this data, share this data. You can animate the data. You can make time series. So there are a number of features. There's a little bit of learning, but once you do that, it's very easy to look at, visualize the data without even downloading the data. You can change colors and range. So there are a number of options here. Another tool is called Giovanni, and this has a number of analysis options. So in here, I have chosen surface temperature from Mehta 2, which is a reanalysis model that I talked about. And here you can choose special domain. So through that, you can choose shapefile for different regions. And I've chosen Washington, DC here. And I'm looking at Washington, DC annual surface temperature from Mehta 2 model. And you can see this is from 2000 to 2024, current month. So you can see this annual cycle, you can see interannual variability, and you can also see this slow trend. If you fit a line here, overall, there's a slight increase in temperature that you can see here. Now, I did not have to download any data. I could just go in here, search for the data, pick the analysis option. You can make maps here as well, scatter plots. I can choose time. I can choose a spatial domain, and then I can do analysis and plot the data. And then I can download the analysis or analyze data in say GeoTIFF formats or NetCDF format or CSV file. So there are a number of options there. These are just some more examples I wanted to show from Worldview. These are fires, the red dots. So this is actually for yesterday, 10th of July, how many fires were there. You can see this is from optical data from MODIS and WIRS flying on Terra, Aqua, and NPP and JPSS models. So you can see how many fires are there. You can also see when there are clouds, it will obscure the surface and you won't have clear data, but wherever it's clear, you can see it. Down here, you can see chlorophyll A concentration. This is from the PACE satellite, which is the most recent satellite that NASA launched. And you can see chlorophyll concentration all over the oceans. And if you zoom in, you will be able to see Gulf of Mexico, Chesapeake Bay. So estuaries you can see from here as well. And the values are given here. Similarly, this is an interesting imagery. This is nightlight imagery from WIRS. This is Texas again, Florida. You can see all these at night. You can see all these cities and lights. Now, 6th of June. Now, if you look at, this is Texas, and this is the blob I'm looking at. This is on 6th of July. And this is on 9th of July, after Hurricane Beryl had already struck this coastal region. And you can clearly see that, I mean, we know that there was a lot of power outages in Texas. And you can see that compared to this, there are areas which are not as bright. So this also provides you a quick way to look at power outages when you zoom in there. This one of the last cases that I want to talk about was there was a fire, Canadian fire last year in May and June in Quebec. It went on for a couple of months. And can you look at pre-fire conditions? That's what we were looking at. June was the most active month, like end of May. So we started looking at, again, surface skin temperature anomalies from MERA in May, and I-merge precipitation anomalies in May as well. So what you do see is that wherever dry and warm anomalies so wherever it is negative anomalies and very dry, those are the regions they are shaded here. And if you look at the firms or fire data, that's where most of the fires actually formed. And this is again from MERA 2. This is the area averaged PM 2.5 data over Washington, DC. Last year, those of you who are from this area would remember that because of the Canadian fire and the wind patterns, a lot of smoke and aerosols came on the east coast of the US all the way. And you do see this May, June, there is very increased PM 2.5 over Washington, DC. This is again averaged over the DC. And then again, it gets back to normal, but clearly you can see. Now, I'm just showing this that these analyses were done with online tools without downloading data. If you want to bulk download data, then you can go to NASA Earth Data Portal and do that as well. So one thing to note about is that GPM I-merge data are available on a cloud-based platform. It's Google Earth Engine. It's free for research, and you have to have some knowledge of Java script programming. But this is showing using I-merge data. We were able to look at anomalies and precipitation which exceeded 90 percentile value over Bhutan. This is one of the trainings that we did, and where there were extreme flooding going on in this red area, and I-merge anomalies and percentile value, that threshold we put, was able to capture exactly the area where there were major floodings going on. Then I want to kind of switch gears. So we looked at all different satellites and sensors very quickly. You have reference tables, which parameters you can get. You also have a number of tools that you can go to and analyze and visualize without downloading the data. You can also download data, bulk download data if you are interested in that. And to really learn this in depth, we have applied remote sensing training program that I want to kind of talk about before we conclude. So RSET, it's a NASA Applied Sciences capacity building program. I'm not sure how many of you, we have trained about 100,000 participants between 2009 and 2023. And you can see the map here, almost like we have 182 countries participants came from, and about 70,000 plus organizations have attended these trainings. So goal is to empower the global community to incorporate Earth observing data into environmental management and decision making, not just research, but also applications such as flood monitoring and mapping, or even drought monitoring and mapping, looking at air quality, looking at climate train or climate change. So that's where the focus is for decision making and management. Can you use this data? How effectively you can use it? And RSET trainings are tailored to the audience. You don't have to have knowledge of remote sensing to take introductory training. There are intermediate and advanced trainings which require some knowledge. Then most of them are online trainings you can register to. There are some in-person trainings which we work with a very special group of people who request specific training for specific topic. And these topics can from these thematic areas. So agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. These are the thematic areas we cover. Trainings are all cost-free. If they're in-person training, there is some cost for hosting it in the sense that venue is needed and participants have to come on their own. But RSET instructors would go there and provide the trainings for free. All the material is available from RSET website. The link is available through here. All the software we use and data we use are open source, so doesn't have to pay for it. Many are bilingual in Spanish for sure, and there are some multilingual trainings in, say, French, and there's one, I think, in Portuguese as well. This is our RSET team that we work together from different NASA centers and put trainings together in different thematic areas. And this is the RSET website. You will have these slides, so you can refer to them. You can look at recording of all the trainings. You can register for the upcoming trainings. There are online resources you can look at. There is fundamental of remote sensing training with self-paced training that you can take. And there's a listserv that you can sign for to stay up to date with what trainings are coming up. So there is also this online resource guidebook has a lot of information. So
Amita,
this is our website you can visit.
Thank you so much. Oh, good. Okay, you're.
Yes, I'm done.
Thank you very, very much. And there's so many wonderful questions. If you take a look, and I see a lot of people are wondering, like, wow, where can I learn more? Because this looks so interesting. That's why I did pull together that resource packet. Jump in there, take a look at that, and then you will see all of those different RSET trainings that Amita was talking about, and all of those are free. So folks, we're going to finish up by getting a feel for, and I've noticed so many of your questions are, very, very specific, or even wondering, well, how do you take all of this information and put it into real world applications? So we're going to be finishing up with Roland Kays, and he is going to walk us through exactly that when it comes to animal research science. So take it away. You're looking great. Thank you so much, Roland.
Great.
Amita.
Great. Thanks, everybody. Happy to have the chance here to talk. My name is Roland Kays. I'm from the North Carolina Museum of Natural Sciences and NC State University. And I'm going to be talking about tracking animals today. So some of the application of how we use the kind of data that you've been hearing about. And I'm going to start with these animals. These animals, you can't see from space. These animals are not detectable from satellites. They're really important. They're doing really interesting things. Many of them are carnivores that are predating on species. Here's a goody that you'll see is being chased down by an ocelot. And these kinds of things are happening all the time. Many of them are rare and endangered species like jaguars and puma. But we can't see these animals from space. They're under the forest, and we don't really know what's going on, where they're going. It's difficult to get these kinds of data. I've shown some examples from camera traps, which are one option. But here's an animal we can see, and that's because it's got a tracking tag on it. This is a white stork from Europe, and you can see it's got a little GPS tag on it. And this allows us to track it from space, right? Using satellites that are going to locate where that GPS unit is, and then also, give us that information back, because who knows where these storks are going to go. And in fact, the storks are a fantastic example because of the amazing journeys that they take that we can map out with this GPS data. So I'm going to show you an animation of some real tracking data. And so we're going to start in Germany. And here comes a stork that was breeding there and now is flying south. And you can see some of the other storks starting to come online. These are all real tracking data as they move their way south during the fall into the winter, doing these amazing crosses over the Sahara Desert incredible journeys. And of course, everywhere they land on the ground, there's other animals that they're interacting with. And here's some examples of real tracking data of wildebeest that we have from some of these same areas, moving in completely different ways. And amazingly, some of these storks keep going all the way down to South Africa, where of course they're going to be interacting with other species like African buffalo, African elephants. This just shows you the kind of information we can collect now from these GPS tracking data, really illuminating where these animals are going, how they're moving around as these storks continue their springward migration north through some of the Middle East, some sort of dangerous places for us to go today, on up back to restart their journey and breed again in Europe. So I think we like this animation because it shows the kind of information that we can get from animal tracking, how country boundaries really mean nothing to these animals, and really the richness of this information that we can get. And so that's why I like to kind of joke around that we're really in the golden age of animal tracking because of the types of information we can get, which really comes from the amazing technology that we can put on these animals, as well as the amazing information we have about the environments that they're moving through from the remote sensing data of the kinds that you just heard. And so that's what I'm going to be talking about today, showing you some examples of what we can learn from tracking animals, and how and why we add remote sensing data, right? Because basically the GPS shows us where these animals are moving, but we need to know what were the conditions at that place. What was the habitat? What was the weather doing at that time? And that's what the remote sensing data gets us. So I'm going to take you back these are early days. This is me trucking around after kinkajous. If you don't know what a kinkajou is, there it is. Basically the cutest mammal ever. They live in the trees, in the rainforest. They only come out at night. They're related to raccoons, but they live kind of more like monkeys. And that's me in grad school tracking them around. And after a year trucking around, this is pre-GPS days, with my radio transmitter, I was able to get about 250, 300 locations per animal, which honestly, I was pretty proud of because I worked hard for that. And that let us learn a little bit about how big of an area these animals use, a little bit about how far they move. But let's fast forward now to modern GPS. The kinkajous are still cute. I'm now older and gray, but look at these amazing data that we can get. This is one animal. It's about 2 months of data. And the color underneath, so the animal is the black lines, that's showing its movement. And the color underneath is canopy cover. And this is some remote sensing data we have on how high the canopy is in this particular area. And so it just shows you the real richness, and we can see, where some of its favorite fruiting trees are, and that it has very, very specific movement routes. And of course, we also have this information in time. And so over on the right is the same movement. And now I'm going to animate this. We're going to see what we call a space-time cube, right? Where time is the z-axis as we rotate this through. So we can start to see how this animal is pretty regularly patrolling its territory, probably defending against other kinkajous as we see these different slices through time of how it's using the forest. And in this case, on that space-time cube, the color is actually their behavior, whether they're moving quickly or whether they settle down for either a sleep or a feed. So this gives you an idea of some of the richness that we can get in today's tracking data. And so what are we asking? Well, typically we want to know, what conditions on Earth do the animals like? What can they survive in? What do they prefer? And especially these days, how are they dealing with all the changes that we're making to the landscape? And I'll show you why this high resolution tracking data is so important. So this is a map of a fisher. A fisher is a member of the weasel family. It's moving around Schenectady, New York. You can see some roads there. You can see a river there. And this is if we had gotten data only every 6 hours. And that number 1 is showing you a lake that looks like it visits a couple times. Number 2 is showing you nothing, that it crosses roads in that's a major road in a couple different places. And 3 is showing, well, it never actually went there. If we zoom into every 1 hour, we can see quite a bit more information. If we actually look at what we had every couple minutes, we can see it never went to that lake. And that 2, there's a really important a road crossing at that point for this animal. And 3, it actually did go there a couple times, but didn't stay very long. So we went to that point number 2, and we found this culvert under the road. And here you can see that animal, Leroy, the fisher. Is this going to play? Oh, it's not playing. Oh, well, it didn't play. But anyway, that's the fisher. And it comes in and out of that little culvert to cross under the road. So that's the kind of detail we were able to discover by getting this really high resolution information to understand their animal behavior, and in this case, how they're dealing with human infrastructure on the landscape. But this is a NASA talk, right? So remote sensing data is what we're interested in. So this is a great animation that we made with the Teton Raptor Center and NASA data showing how golden eagles are migrating north with the green up. So you can see as the snow is going away and the vegetation is turning green in the spring, these animals are moving north. And so we can start to map out this. And of course, this is just an animation, but we can download all the data, do our analyses to start to predict where they're moving around, how they're affected, how they're timing their migration. As here comes the snow, they're headed south, and we can start to see how they're timing that. And now also, of course, start to think about how this might change with global warming. So this is a great animation we did with the Teton Raptor Center tracking golden eagles. And here's another one. Let me orient you here. In this case, green is ocean, black is land. So we've got Galapagos. That red dot is an albatross, and I'm going to animate these albatrosses flying between Galapagos and the coast of South America. And now we've got wind and ocean productivity. So those vector lines are showing you the wind. So you can see they're riding the wind to the coast, and they have to fight the wind to come back to the Galapagos. Why are they going to the coast? Look at that ocean productivity. That's where the most productive waters are. So it's worth it for them to fly all the way to the coast, fish in those really productive areas, and then head back to where they're nesting, their safe nesting ground on the Galapagos. So this is an example of how we can start to overlay multiple different layers on top of the animal tracking data, really start to understand why animals are going places and how they're getting there, either riding the wind or fighting the wind. Okay, I want to show you, I'm jumping around species here, but now we're up to the Yukon with some caribou. And we've been working with the Northwest Territories and Yukon wildlife biologists who want to know when the caribou have young. And so these boxes are just showing you some of our analysis. We have an analysis tool where we get the data and we filter it to the time of year when they might be having young. And then we run this partition cluster detection. So partition, it means they had a baby. And what we find is over on the left is showing animal movement speed. So guess what? When you're a female caribou and you have a baby, you stop moving because your baby can't keep up. So we can see that in the data and say, hey, look, she stopped moving. She probably had a baby. And then we can map on the location where that is. And we can also look on the displacement. And so we can start to see where they're having their babies. And now I'm going to animate that on top of the changing remote sensing data. So this is NDVI. It's a measure of vegetation greenness. Those purple dots are female caribou. And every time a blue dot shows up, means they popped out a baby. So now we're able to map out where these birthing events happen, which of course is super important habitats. If we're going to conserve habitats, the birthing grounds of caribou herds is some of the most important. So we can start to see where those are and what to measure their conditions with remote sensing data. We can also do multiple animals at once at the same time, which we kind of had with those caribou. But let's jump over to Africa and look at some baboons with Meg Crowfoot. And here comes the troop of baboons running up the road and running over to this green glade. Some want to go north, some want to go south, and they end up going north together. So Meg's been using this information to look at how animals are making decisions, how groups of animals are making decisions. And in the case of baboons, they actually vote. Whichever side the most animals go to, the other animals go along. And of course, the baboons need to stick together because there's leopards and lions in this habitat. And we can also put sensors on the animal tags themselves. So here we're back to some white storks, and this is some data from Martin Wikelski in Germany. And of course, they ride thermals, right? So here's a bunch of storks flying together and riding thermals. Each color is a different stork. But you see those blue wispy dots? That's wind speed measured from sonic anemometers, little wind gauges on the tags themselves. So we can see this crosswind that's pushing them a little bit to the side as they ride up to this thermal to get the elevation, then they're going to cruise down. And we're actually working with some weather agencies now to share this information of the wind speed at elevation at a known location from a stork, which is basically what they get from weather balloons. Only these storks are flying around all over the place all the time. So it's not just one weather balloon out. And so we're looking to help connect that information to help them forecast weather. What's next? We can also do multiple species at the same time. This is we're in Panama, just some examples of study we were doing on a bunch of different fruit-eating mammals. The kinkajous are out at night. We saw a kinkajou at the beginning of the talk. They're the purple dots. And during the day, we've got coati spider monkeys and capuchin monkeys, and we're using these in combination with some drone data on where the fruit trees are to see if the big brain primates are better at finding food than the kinkajous and the coatis that have smaller brain size. So how do we do all this work? A lot of it is done with the help of this tool called MoveBank. This is a big data archive. It's got over 6 billion records of animal tracking data. We stream in 3 billion records every day from animals all around the world, coming in through cell phone networks, IoT networks, satellite communication networks. And all these studies are done by biologists all around the world, and they retain complete control over the data. So you can go to MoveBank and you can look at some data. In this case, the blue and red dots are studies that I have permission to see, and the gray dots are studies that I don't have permission to see, but I could ask for permission. Because, of course, some of this data is very sensitive, right? Knowing where golden eagle nests are or where elephants are at any one particular moment with live data, we can't necessarily leave that open to the public, but sometimes we can. We also have an app. I should have put the app up. It's called Animal Tracker. You can get it on your phone, and there's lots of live animal data there as well. So check out the Animal Tracker app. And so MoveBank also is meant to be an archive. And this is just an illustration of an archive that we put together with Arctic data. This is 15 million locations from 96 different species collected over 30 years. So, of course, the Arctic is changing really fast now with the climate, and we wanted to document this with animals using the animal data to see how they're responding. And so we put these data together. They're available for research. So if you're a scientist and you're interested in this, some of it's also available public. You can get at that. So that's an example of that project. So I'll wrap up now and just acknowledge there's a big team behind the MoveBank work with the Max Planck Institute and lots of different organizations, including NASA, that help fund our work, and lots of collaborators that are sharing their data for us to show some of these animations. And I'll just end with this screen now, which is a global representation of a whole bunch of different migrating species. These are, again, real tracking data that are in MoveBank, showing, again, how animals know no boundaries and how amazing our planet is. And I don't know if we're taking questions in this thing or not, but that's the end of my talk. So thank you very much.
Wow. Thank you so much. If you still have a little bit of time, Roland, if you take a look at the chat, I did let people know because there were a lot of questions. You got people extremely excited thinking about the potential of all of these data, and also just the idea that we're able to follow apes and see how they're making these decisions, and monkeys, and it's simply an incredible use of these data, and also the fact that people are able to come on here and look at other people's data and share. This is a brilliant example of open data that has been around now for many years before the term open data and citizen science got to be kind of cool. So if you'll take a look at the chat and answer a couple of the questions, but I also put, because I made the resource packet, I want some people to do their own work and their own research. So if you're wondering about what kind of animals can be tracked and how do they do this and what are some of the opportunities, do take a look at the resource packet and go to the MoveBank site. I highly recommend. I have on my cell phone, I have downloaded the MoveBank app because it just really is absolutely fascinating. I know I come away from these webinars feeling inspired, in spite of all the wicked problems that we have in this world. When you look at the ways that people are coming together all around the world, the same way that all of you have come all around the world this evening, from fourth graders all the way up to lifelong learners. It's truly inspiring. So we hope that you'll take a chance to dig into this resource packet, that you will take a look when you get a chance at many of the resources. You may want to watch this webinar again. And I will also ask the presenters if it's possible for me to get their presentations. I'll put them in, of course, PDF and put them up on our website as well, because I can tell a lot of people, just want to have some time to get in here and study this on their own. Roland, thank you so much. And Amita, I know Sarah had to go because she has an early flight all the way out there to Japan in the morning. And also Andi, thank all of you. And then, of course, in the background, we've got Andrea Portier, who's just kind of holding up all the scaffolding and being the Wizard of Oz in the back there. So we'll stay on. We'll probably stop the recording. Well, maybe we'll keep it going for a couple minutes so that we can be getting the information that's in the chat. But if we don't get a chance to answer your questions, be sure to take a look at the resource packet, and also be sure to join us next month when we're going to be doing a deep dive into data. You know, what is data? What does it mean when we talk about open science data? We're going to learn from an Earth to Sky, our Earth to Sky coordinator who works with national park interpreters, about how data is then being shared with national park interpreters, and then being they take it and they translate it, interpret it, so that people who come to visit their parks can get a broader understanding of the impact of, in this case, climate and climate change on the beautiful national parks that people are going to visit. So really, truly amazing, all the things that are being done. And it's so much fun to take a look at these wonderful comments and questions from people in the chat. Thank you very much. And thank you to all of you. You are all simply amazing in the fact that you're here spending your time from around the world. Just really shows the power of you know, the fact that we're going to be able to solve some of these wicked problems. And a lot of that is going to take learning, listening to each other, learning, delving into some of this content. Some of that will mean self-study, and that's why we do now have so much that's accessible on the internet. And then, of course, as you get into some of these courses and you get into some of this content, you'll start to find people who are available to engage with you and to answer your questions. And hopefully you'll also work on taking more classes, learning more about these things that interest you. So you are all so welcome. And from the bottom of my heart, I thank you for joining us. I never cease to be amazed by the fact that, like tonight, we had 178 people on this webinar to learn about something as complex as remote sensing. I mean, that's huge. You guys like so rock.